So what I thought was I will introduce the Eurocode based design first and cover the general aspects, and then we'll go into the more specific foundation related designs. So I'll share the screen. So we'll start by covering the basics and discuss a little bit about Eurocode applications, basically Eurocode 2, and then we'll learn about the design of beams for flexure, shear, and also torsion. And then we'll also look at other related aspects like punching shear and so on. And once we cover sufficient ground on the general design principles, we'll move on to the specific applications in foundations. So that's the way I have thought of organizing the lecture series, especially because there may be few who may be less familiar with the structural design. So we'll go on the general applications first, and then move on to more specific details. So if you take a structure, before that, can you see the screen?
Yes, sir.
Yeah. So somebody, one or two would have to give some response. Otherwise, it's difficult for me to judge whether you are getting the information. Right. So if you consider any structure, we have to consider self-weight, the load of finishers, and so on. And those are called, earlier we used to call them permanent loads, so dead loads and superimposed dead loads. But in Eurocode, they are called actions. So we get permanent actions and variable actions. So permanent actions are the permanent loads and variable actions are the variable loads. So permanent actions are due to finishers, services, self-weight, and any other load of permanent nature. And variable, and also partition loads. And variable actions will be due to the live loads. And in addition to that, wind loads, snow loads, all these other loads are also considered as variable actions. So the way that these permanent actions and variable actions are combined in Eurocode is can be slightly different. So we'll have a brief look at that as well. So when you look at loads on a structure, we have to, when to get the most critical combinations, we have to combine the permanent actions and the variable actions. And when you are combining, there is a possibility that the vertical loads, like the weight of furniture, people, which are acting in vertical direction, may act simultaneously with the lateral loads, like wind loads or even earthquake loads. So there's a possibility that the vertical loads will act with the horizontal loads. And to take account of that, we have to combine the loads. So the way that Eurocode allows us to combine the loads is that you have to multiply the characteristic loads by the appropriate partial factor, gamma f. And then when you are looking at the variable actions, we consider only one of the actions as primary action, and the others are considered as secondary actions. So when it comes to the variable actions or live loads, we consider only one variable action as the primary. So if you are considering the vertical loads as primary action, then the wind loads will become the secondary action. If the wind loads are the primary action, this can become the secondary action. So the difference between primary action and the secondary action is, when it comes to the primary action, we consider at 100% of the action is effective with the partial factor. And then when it comes to the other loads, we consider the partial factor is there, but there's an additional reduction factor that will consider the fact that all the maximum loads cannot act simultaneously. So to consider that all the actions cannot occur simultaneously, we'll have an additional factor phi naught. So we'll look at this in a little more detail in a moment. And if you have any questions, you can ask the questions as well. So if you look at these factors, for permanent actions, we get dead loads or any permanent load. We have a partial factor of 1.35, and variable loads, we generally have a factor of 1.5. So in BS codes, it used to be 1.4 and 1.6, but in Eurocodes, it's 1.35 and 1.5. And then if you look at this equation, and you can see there's a phi naught factor. And if you look at this table, you can see the value for phi naught depends on the type of usage. If it is an office building or a domestic building, phi naught will be 0.7. Whereas if you are using this particular area for storage, then there's a possibility that in the case of storage, the full effect could be there when the other loads are acting. So because in storage, you might store goods to the full capacity. So because of that reason, we use a value of 1. We don't use any reduction. And when it comes to wind loads, you can see the factor that we use is 0.5. The factor that we use is 0.5. So if you want to combine the dead load, here you get a factor of 1.35. So here you get 1.35. For live loads, so variable actions, the vertical loads, you get 1.5. So here you get 1.5. And if you are going to combine it with wind loads, then here also you get 1.5, but you have to multiply it by 0.5. The reason is, for wind loads, phi naught factor is 0.5. For wind loads, phi naught factor is 0.5. So you'll multiply this by 0.5, and then you'll get the full effect. So the load combination will be 1.35 GK plus 1.5 QK1 plus 1.5 into 0.5 times WK wind, and 1.5 into 0.5 is 0.75 times WK. On the other hand, you can consider the primary action is wind, the secondary action is vertical load. So if this is the primary action, here you get 1.35 GK plus 1.5 times WK plus 1.5 multiplied by phi naught for vertical loads like domestic and residential area, the variable actions. This value is 0.7. So here you get 0.7 multiplied by QK. So 1.5 into 0.7 will be 1.05. So that way, the Eurocodes allow us to consider different combinations with some reduction in the load applied, and we apply the full load only for the primary variable load, and for the secondary variable loads we use a lesser value. So I will show you another example of that in a moment. Now let's have a look at this particular example of a shear wall. So on this shear wall, when the wind loads are acting from this side, this is a side that can go into tension, and this is a side that will go into compression. Because the load is acting from this direction, there will be a bending moment acting this way, and that bending moment will give compression on this side, tension on this side. So that's what's going to happen. And then we want to see the worst effect on this wall, and the worst effect on this wall is some tension occurring here, because if there's any tension here, that tension can be transmitted to the foundation as well. And transferring tension to the foundation may not be desirable, because when you transfer tension, the foundation might not transfer any load to the soil. So if the tension is high enough, then you might find that the foundation is now not transferring any load to the soil. So we always like to have no tension here. So to get no tension, we have to have minimum load here vertically and maximum moment and maximum moment. So when we want to get that situation, we might go with this particular load combination, and we have only the self weight of the structure and also the wind load. So we maximize the wind load by applying a factor of 1.5, but we keep the vertical load minimum by applying only the permanent loads. But even for the permanent loads, we use a factor of 1.0, a factor of 1.0. So if you want, you can keep your mics muted. Then you can minimize any disturbance. And whenever you want to talk, press the space bar and talk. If you want to talk, you can just press the space bar, keep the space bar pressed down, and then you can talk. You don't have to unmute and talk. You can just press the space bar whenever you are talking. Then that way you can, keep the mics muted. And whenever you want to talk, just press the space bar and talk. And if you want to ask a question, just press the space bar, keep it pressed down, and then you can talk. And if you want to talk longer, then you can unmute the mic as well. So then we also have to look at what happens here on the compression side. And compression side, there can be two situations. One is the permanent load is anyway acting, and the variable vertical load also can go into a maximum. And when this is happening, we are getting a wind load. Wind also acting on the structure. So that means, vertical loads are maximum and wind is also acting simultaneously on the structure. Or the other option is wind is acting at full intensity. Vertical load is anyway there, that is the permanent load. But when it comes to the variable load, we allow a reduction. So you can see this particular case, we are considering the vertical loads are all at maximum. The wind loads is 1.5 times 0.5. And why you get 0.5 is because of this reason. For wind loads, phi naught factor is 0.5. And if you look at this equation, you can see we have to multiply the secondary variable action by phi naught. Secondary variable action should be multiplied by phi naught. So that is one of the load combinations. And then the other combination will be dead plus impulse plus wind. Now in this case, dead and wind are at the maximum. Then impulse load becomes the secondary variable load. And for impulse load, the partial factor is 1.5 and the reduction factor phi naught is 0.7. Phi naught is 0.7. Mostly 0.7, except a building used for storage facility. So when you do that, you will end up with this combination. So this way, you can actually create different load combinations for a structure. And so if you have a building, I'm actually trying to get this screen. Right. So now you can see the screen, is that right? So basically what happens is, so if you have a building, you get GK and can also get UK, and you can also get WK. So if you want to get the combinations, to get the maximum tension on this side, maximum compression, we can get 1.35 GK plus 1.5 QK plus 1.5 into 0.5 WK. So which comes to 1.35 GK plus 1.5 QK plus 0.75 WK. That's one of the combinations. And it's also possible to get the maximum compression here with 1.35 GK plus 1.5 into 0.7 times QK plus 1.5 times WK. And in addition to that, we can have a case where we have only the dead load and the imposed load. But now you see, this combination will be more critical than this one. So this can be more critical than this one. But still, you know, we include this as a combination. The reason is, you know, sometimes we like to see what is the effect of dead and imposed loads, or the vertical loads, only the no wind loads. If you like to see what is the effect of vertical loads only, then it's useful to have this particular combination as well. So we might use this combination, but you can clearly see this can be more critical than this combination. So the other option is, here you'll get tension, and tension will occur when you get 1.0 GK plus 1.5 times W. So the tension will occur only due to that case. So this way, we can say this is case 1, and we might say this is case 2, and this is case 3. This might become case 4. So we can have clearly about 4 cases: case 1, case 2, case 3, case 4. So this way we can create the most adverse conditions for the loading, which can be used for design purposes. Is that clear to you? How to make use of these different factors? Can somebody give some feedback? Or if you have any question, you can ask. Is it clear? Who is going to respond? Nuranjit? Are you there?
Yes, sir. Clear about it.
It's clear. Is that right?
Yeah.
Tamira?
Yes, sir, clear.
It's clear, right? Okay. Now, so in addition to that, when you are designing beams, you have to actually create pattern loading. You have to consider pattern loading. So one of the differences in Eurocode is, when you are creating the pattern loading, when it comes to the permanent action, all spans you will use the same variable action partial factor. So the factor is 1.35, 1.35, 1.35. And you might argue that, by using 1.35, you are not getting the most critical effect here. But what is given in the Eurocode is the unfavorable and favorable factor should be used so as to produce the most onerous condition. Generally, permanent actions from a single load source may be multiplied by either an unfavorable or favorable factor. So you will have only one factor. If you are using 1.0, considering that it's not a favorable load, and do you know what is the difference between favorable and unfavorable loads? So basically, if something is going to improve the stability, then we say it's a favorable load. And if something is going to make it worse, then it's an unfavorable condition. So when you are considering the dead weight in the beam, then the unfavorable condition is 1.35 GK. So if you have decided to use 1.35 GK and get the bending moment envelope, then everywhere you will use 1.35. Whereas if you have decided to use 1.0 here, then here also you will use 1.0 GK. So if you decide to use 1.0 here also you should use 1.0. So this is one of the variations that you can see in Eurocodes. So you will always see that, the most favorable, unfavorable action is used in every span, or the most favorable action is used every span. But when it comes to the variable load, you can always have no variable load here and the maximum variable load here. That is possible. But when it comes to the permanent actions, if you are using 1.35, considering that it is when it is loaded minimum, this side is loaded maximum, here you get some hogging moment and so on. So then you might say, it's better to use 1.0 GK plus 0 QK. But the Eurocode says if you are using 1.35 here also it should be 1.35. On the other hand, if you are using 1.0 here also should be 1.0. So that is one of the things that you have to consider. And so basically, when you are designing for the vertical loads, generally we make use of simplified subframes. And when you are using simplified subframes, you are having maximum load here, minimum load here, maximum load here. This will be 1.35 GK plus 1.5 QK. And this will be 1.35 GK plus 0. Because the variable load we consider as 0. And it's also possible to have another case where you have the maximum here, minimum here. And this minimum again will be 1.35 GK plus 1.0 times QK. And the maximum will be 1.5 GK plus 1.5 1.35 GK plus 1.35 GK plus 1.5. So you have to create this, and when this is loaded with maximum, here you get the maximum sagging here, and when you get the sagging as maximum, there's a possibility that this span might go into hogging moments. And that's why, you know, we go with pattern loading. And then we load this on maximum and expect this to have the minimum moment here. So when you are considering the pattern loading, either you use 1.0, 1.35, but whatever you will use it throughout all the spans that you are going to design. Right. So that is a brief introduction to the loading that you have to consider when you are designing the superstructure. And these loadings will finally be transferred to the foundation as well. Right. Then we look at the design of reinforced concrete. And so if you are going to use Eurocodes, we have to rely on the cube strength. We have to rely on the cube strength. But fortunately, they are given the cube strength as well. So if you look at this particular table that is obtained from the Eurocode on page 29, table 3.1. So these are the extract from table 3.1 of Eurocode 2. And here you can see the concrete strengths, the cylinder strengths are given here. The corresponding cube strength is given here. So the general relationship is, you know, cube strength, cylinder strength is only about 80% of the cube strength. But the question is, which one gives the correct strength? Cube strength or the cylinder strength? Which one gives the actual strength, the real strength? Can somebody answer? Which one gives the actual strength of concrete? Cube strength or the cylinder strength? The answer is cylinder strength. Then the next question is, why? Now, you know, when you are testing a cube, we have a thick steel plate here. We have another thick steel plate here. So these plates can actually restrain the expansion of concrete. So what actually happens in the cube testing is, you are applying a load in the vertical direction. And you know, when you apply a load in the vertical direction, there will be an expansion in the lateral direction. So if the compressive strength is sigma, here you get a tensile stress of nu times sigma, where nu is the Poisson's ratio. So where nu is the Poisson's ratio, so you get nu times sigma, you get nu times sigma acting in the transverse direction. Then what happens is, due to the presence of these steel plates, the effect of this nu times sigma would be reduced. So finally, you will end up with a higher strength for concrete than the actual strength in the structure. You will end up with a concrete with a higher strength than the actual strength that you get in the real structure. Whereas when it comes to the cylinders, cylinder height is 300 millimeter. Here it's only 150. So because the height of the cylinder is 300 millimeters, the effect of these platens or the steel plates would be less. So the effect will be less due to the steel plates. So you tend to get the actual strength in cylinder testing. So that's why, you know, two values are given. One is for the cube, the other one is for the cylinder. And when the cylinder strength is 25 newtons per millimeter squared, when the cylinder strength is 25 newtons per meter squared, the corresponding cube should give a value of 30 newtons per millimeter squared. So the cube strength gives a higher value than the actual strength, whereas the cylinder strength gives the exact value. Is that clear? Is it clear?
Yes.
Right. You can just press the space bar and talk. You don't have to unmute. Just press the space bar when you are talking. And in addition to those properties, some tensile properties are also given. And these notations will have different, will have a set of meaning. But only thing is, these are used in different equations, so we will not worry about it. And if these FCTM and this FCTK and this FCTK is the value that you get as the characteristic strength. And here again, FCK is the characteristic strength of the cylinder. So what you see is that for different concrete types, either you can go with the cylinder strength or the cube strength. So you have to be very specific because there's a difference. You can get other important parameters like the tensile strength, elastic modulus, and so on. And in addition to all this, you'll also get other important property, and that is the elongation that you are going to get when the concrete is about to fail. And you all know that concrete is a material. After hardening, when you apply the loads, concrete will initially behave more or less as an elastic material. When the stresses are fairly low, it will behave as an elastic material, almost a linear relationship with stress and strain. And as the stresses are higher, then you will find now the strains are going to be increasing. Even for a smaller strain increase, there can be a significant increase in the strain. And when the strain is 0.002, there will not be an increase in load thereafter. The reason is by that time the micro cracks will start forming, and when there are micro cracks, concrete cannot take any more load, and then what happens is the strain will increase until the cylinder crushes. And we say the maximum strain by the time that the concrete is going to fail is 0.0035. Whereas it will become a rectangular stress block after strain of 0.002. So those are the important parameters with respect to the stress strain curve of concrete. And this particular stress strain curve is valid up to 60 megapascal cube strength or 50 megapascal cylinder strength. So if you are designing a structure having say a concrete grade of 30, then you can make use of this particular stress strain curve. But if you have decided to go for a very high strength, then you'll find some of these values will need some adjustment so that it will take into account the fact that when the concrete is very high strength, all the pores in the concrete are filled up with various very fine materials that we use to obtain the high strength. And because of that reason, the concrete tend to be little more brittle than the low strength concrete. So higher strength concretes tend to be little extra brittle than the normal weight concrete. So because of that reason, you have to take that into account, and how you take that into account is by modifying this stress strain curve. So this stress strain curve is valid up to 60 megapascal cube strength or 50 megapascal cylinder strength. And then you can also see another important parameter, this 0.85. And FCK is the characteristic strength of concrete. And we learned that, you know, cylinder strength is equal to cube strength. But you can still see there's another factor called 0.85. And what is the purpose of this factor? And here you can see 0.85 allows for the long-term effects and the difference between cylinder crushing strength of concrete and the bending strength. When you use concrete in reinforced concrete members, most of the time you will find that the behavior has something to do with flexure, even in a column. Even in a column, there can be a bending moment acting on the column. So because of that reason, you know, we have to always think about the behavior of concrete in flexure to relate the behavior of concrete under pure axial load and the bending induced forces. We use this factor 0.85. So this is the factor that is used in British courts, and they use a factor of 0.85. So BSEN version, you'll find that, you know, the concrete strength, the concrete cylinder strength is reduced by 15%. And then you divide it by the partial factor. When you do all this, you'll end up getting the strength of concrete. And the strength of concrete that we use for our calculations is called FD, FCD, and the value of FCD is given by this equation. So the strength of concrete that we use for calculations is 0.567 times cylinder strength. So the strength that we use for our calculations will be 0.567 times the cylinder strength. Is that clear? So we need a factor of 1.5, that is the partial factor for material strength. And we also need another parameter, and that is 0.85. And this 0.85 will relate the behavior in compression to behavior in flexure, but behavior under flexural compression. And you can also see these parameters are applicable up to 50 cylinder strength or 60 cube strength. So shall we take a break of about 10 minutes and meet again at 5 minutes past 3? because we are supposed to give a break of 10 minutes after every 50 minutes when you are doing the Zooms. So shall we meet at 5 minutes past 3?
Okay, sir.
Yeah.
Okay.
So I'll stop share and stop share. And stop recording also.